Right, welcome to London Learning Lean. Next week, just to warn you, we're celebrating 70 years of the Queen on the throne, and so there won't be any seminar. In 2 weeks' time, it's Sebastian Monet telling us about the Kroll topology. But this week, we're very pleased to have all the way from the London School of Geometry and Number Theory, David Ang, who is going to tell us about his work on the Mordell-Weil theorem.
Thank you, Kevin. So this is a project that I was meant to do for the London School of Geometry and Number Theory mini project. It's my very first project. Yeah, and this is my first lean project I've ever done. So some of the design decisions that I've made might not be the best, but let's try to see what I've done. Yeah, so wait, I can't click. Yeah. So yeah, this is an overview. So I'll try to, so the first part will be a quick definition. Well, it's not really quick, but I'll try to describe what elliptic curves are. I'll give a very abstract definition. If you don't know what that is, that's fine. I'll give a concrete definition. I'll try to describe the implementation and what's wrong with associativity and why it's so hard. Then the second half, I'll try to give an outline of the proof of the Mordell-Weil theorem, which is like a fundamental theorem in the theory of elliptic curves over number fields. Right. Yeah. So what are elliptic curves? So essentially, it's a curve. You have a polynomial equation in y and x, and you have some fixed constants a and b in some ring or some field. And a curve is just a solution, the set of all solutions to a polynomial equation like that. What does it look like? Well, it looks like that. If you try to graph that curve in a real plane, it will look something like this. So it's a curve, right? But there's also an important property. It's a group, right? So there's some kind of notion of addition of points. Take 2 points on your curve, and there's some way of like adding the points to make a group. Yeah. Why do we care about these things? Okay, so I'm gonna give a very brief but like I'm going to state a bunch of applications. Right? So mainly the 2 applications is in cryptography and in mathematics. So in cryptography, there are like, we try to make methods, make systems, make protocols to make cryptography work. And sometimes we want to try to test our protocols on why something works or why something is not so good. So for instance, there's this thing called the RSA, but there are also methods in elliptic curves that counter RSA. So in some sense, if you have a method to do integer factorization, that kind of breaks RSA. And elliptic curves have this, there's this application to trying to do integer factorization using Lenstra method. That's like really fast. So in some sense, it breaks RSA, but not really. There are also like a few other applications, like when you try to do Diffie-Hellman. So Diffie-Hellman is basically a cryptographic scheme that is involved that involves this problem called the discrete logarithm problem. It's a hard problem that's not really there are not many good ways to solve it. The idea is you have given P and Q, you want to you want to obtain, well, that's kind of true. You want to obtain the n such that n times Q is equal to P. And that's not so obvious how to do. If you care about post-quantum cryptography, like what it means to be post-quantum. So once quantum computers are a thing, it's hard to know what cryptographic systems still manage to hold. There are methods. There's this thing called the super singular isogeny Diffie-Hellman. I just put SIDH. That involves this theory of like isogenies of elliptic curves, isogeny graphs of elliptic curves. And it's apparently post-quantum secure, even though we don't really have good quantum computers good enough to like check whether this is okay or not. So that's cryptography. We care about the mathematics, right? So in number theory and algebraic geometry, like elliptic curves are in some sense the simplest non-trivial objects in algebraic geometry. So you can define it in several ways. Like you can call it a abelian variety of dimension 1 or a projective curve of genus 1 with a fixed point, etc. Right. So like we know conics, but the theory of elliptic curves, the curves of genus 1 is not, we still have lots and lots of open problems that we don't really know the answer to. I mean, there's this, well, everyone knows about the Fermat's last theorem, right? Fermat's last theorem is essentially saying that whenever you have an equation like this, where P is greater than 2, well, you can't find solutions to equations like that. And the idea, the very high level overview is that associated to that equation is an elliptic curve over Q, and it's shown that it can't be modular. But there's a result called the modularity theorem that says that all rational curves are modular, which means you get a contradiction. So such a thing cannot exist. You also like all these results and all these conjectures about ranks of elliptic curves. So I haven't said what this rank is, but I'll define it near the end. Whether you know that the rank is bounded or not, what is the average rank of an elliptic curve, and stuff like that. And you also have this conjecture, which is a Millennium Prize puzzle, that the analytic rank, whatever that is, equals to the algebraic rank of an elliptic curve. Yeah, so all these things are just like some cool applications or cool things that people are working on these days. Okay, so now for the next two slides, I'm going to give a definition of an elliptic curve, but I'm going to give a very abstract definition that nobody will understand. That is fine, because I'm trying to just motivate what's going on and why. I mean, in Math League, we want to have a very general definition of things. So I'm trying to define this over a scheme. Okay, if you don't know what a scheme is, that's fine. It's just a geometric thing. So an elliptic curve over a scheme is a diagram. So basically, you take a map from E. So E is a scheme and S is a scheme. There's a diagram in the category of schemes from E to F, from E to S, and you have a map going up. Okay, so that's an elliptic curve, plus a bunch of technical conditions. Okay, that is not so visible, but yeah. So basically, you have like the fact that F is smooth, proper, and all its geometric fibers are integral curves of genus 1. Whatever that is, that doesn't really matter. The point is that it's basically a diagram going up, down, and going up. The thing going up is a section. Okay, so like I've given you what the curve is, what the scheme is, the geometric thing, and what is a group. So for any scheme P over S, I can define the set of T points of E. So this is just in the category of schemes, I'm looking at all the morphisms from T to E in the category of S schemes. So that's like a set. And I can make this into a group by identifying it with another thing, which I'm going to call a Picard group. And this thing is a group. Okay, I didn't tell you what the definition of this thing is. I tried to tell you what the definition of this thing is, but that is not really that important, because I'm going to say what it is explicitly in the next slide. All right, so this defines a functor from the category of S schemes to the category of abelian groups by sending T to the set of T points. Yeah, so it's a good definition for algebraic geometry. I mean, typically you want to play around with all these like very abstract notions in category theory. But our problem is I said it's an equation. Where's the equation? What's going on here? What is this absolutely abstract definition? It's useless. Okay, so instead of working over a scheme, maybe you will make it more concrete by working over a field. Okay, so let S be a spectrum of a field and T be a spectrum of another field. So if you don't know what that means, think of it as a field extension. But if you know what that means, that basically says the S and T, this is a point, right? So if you have a map going down and you have a map going up, this is a point, means that this 0 chooses a point in E, which means is basically you have an E and you have a point 0 that is chosen by the section going up, right? So here E is a nice genus 1 curve. I said the nice thing comes from like all these technical conditions, and O is a point in E defined over F, right? Okay, still this thing is still kind of abstract. It's kind of useless. But the point is now the Picard group, I can tell you what the description of the Picard group is. So this is a group, right? There's a bunch of, so this is defined to be, this is defined to be a bunch of divisors over E of E over K. So this is divisors can be defined using algebraic geometry over principal divisors, right? So I can give you a description of this thing, and this is naturally a group. So this is a group, right? So then using this description, now instead of a functor from the category of S schemes to abelian groups, you get a functor from the category of F algebras to abelian groups by sending K to the K points of E. Okay, so now this group law is free because I told you what the group is exactly. But the problem is we don't have equations. So what's going on? Okay, so if you don't understand anything from these two slides, it's fine, because I'm going to tell you what the equations are exactly. So the idea is, from the stuff from the previous slide and the stuff that has equations, these two things are linked by what's called the Riemann Rock theorem. So a corollary of Riemann Rock says that an elliptic curve is a plane curve given by such an equation. So this is defined in a projective plane with homogeneous coordinates x, y, and z. Right, so now you're working over projective space, and there are 5 coefficients: a1, a2, a3, a4, and a6. Don't ask me why a5 is not present. It's just a convention. Right, so Riemann Rock says that it's basically this thing. Right? But recall we had a bunch of like technical conditions being smooth, proper, and stuff like that. That's all collapsed to one thing. There's a quantity called delta, and delta is given by that, but don't worry. There's just some humongous thing, which is usually called the discriminant, right? And then the fact that it's smooth and all these extra technical conditions just says that we require delta to be non-zero. Okay, so that is basically what an elliptic curve is. If you don't remember whatever I said earlier, this is the definition. Right, if the characteristic of your field is not 2 or 3, you can complete the square. You can erase these two things. You can move these things to the other side, and you get something y squared z equals to some huge thing. If it's not 3, you can complete the cube, and then you can erase this term. So what you're left with, what you're left with is just this term, this term, this term, and this term. I'm going to call A and B, okay, so to make it easier. Right, and then now I have this huge discriminant, this huge nonsense. What does this become? Oh, this just becomes that. That's nice. Right. Yeah, so this was the thing I promised in the very first slide, right? But the issue is, in the first slide, I had y and x. Now I have y, x, and z. So what's going on? Right. So y, x, and z, they are homogeneous coordinates in projective space. The issue, the point is that in the first slide, I said x, y, and z I can draw on the affine plane. So in fact, I can, if I look at the point at infinity separately from the affine points, I can actually remove the z. So if I let z be 0, then this is 0, this is 0, this is 0. So x is 0. So in fact, if z is 0, x is 0, and in homogeneous coordinates, that means you only have one point. Y can be anything. Right, so that means there's only one point at infinity, and I'll call that point 0. So I call it 0 because in some sense, it behaves like the identity. It will be the identity in the group law. So the group law, right? So recall, I always said there's a curve and then there's a group. So what's the group here? I define the curve. The group is given by this Picard group. So instead of telling you what divisors are, I'll tell you how it is given directly in terms of the picture of EK, right? So the idea is that the operations in the group law are characterized by a property that we want. Is that if you have 3 points, P, Q, and R, they must add up to 0 precisely if they are collinear. Okay, so I just gave you a characterization. What's the definition of the addition? Okay, let me draw some pictures. Okay, so imagine I have 2 points, P and Q. How do I add P plus Q? I draw a line across P and Q. You intersect the curve at some other point, then I reflect it. That is P plus Q. So this exactly satisfies this condition. And this also says that if you want to do an inverse of something, you just flip it over, if that makes any sense. Flip it over the x-axis. Okay, so yeah. What if P and Q are the same point? If P and Q are the same point, which let's say P, you draw the tangent line at this point, you intersect the curve at another point and reflect it. So this is P plus P, or 2P. What happens if this point is not, the tangent line over this point is not, that does not intersect the curve at a third point? That is only possible if this point is exactly here, right? So if this point is here, the tangent line will be vertical. then it will not intersect the curve at the third point. Right. So if it does not, so this is what I'm saying now. Right? If this is in here, which means if it gets killed by, right, let me repeat that. A point gets killed by 2 if and only if y is equal to 0. Right. So because if a point is in here, the tangent line will intersect nowhere. Right. So it must intersect this point and the point at infinity, which is basically, you can imagine it as the thing at the top. At infinity, right? And then that is in the 2 torsion subgroup, which I'll write E2, if and only if the y coordinate is 0, which means it lies in the x-axis, and vice versa. Okay, so maybe you didn't get what I'm saying. Okay, I just said a bunch of, just ranted a bit, but the main point of all this is that there are many cases you need to check when you try to define addition, but all these cases are completely explicit. So they are defined by lines and curves, and you're solving equations. Yeah, everything is defined in terms of equations and a bunch of if then else statements. Okay, yeah. So I have given 3 definitions, right? Three of these definitions. 2 of them are very abstract, and one of them I try to give it as concrete as possible. The problem is, we would like to do it as general as possible. So we like to actually define 1 in lean. But unfortunately, that's not quite possible. Okay, so this is the generality, right? So 2 and 3 are the same by the Riemann Rock theorem. Well, 1 is a more general definition. We like to do 1. But unfortunately, 1 is not really possible. We need to define all these notions of properness. I mean, genus is a quantity defined using cohomology. It's not really realistic. And 1 and so 2 is also kind of hard because you need you need the notion of genus, right? I think 2 is defined in terms of genus. The fact that 2 and 3 are equal, so this is the fact that 2 and 3 are equal, is by the Riemann Rock theorem. And the Riemann Rock theorem requires you to say what it means to be a divisor, what it means to be a canonical divisor, what is a differential and stuff like that. And that's not really realistic. But the definition of 3 is concrete. It's just 5 coefficients, right? A1, A2, A3, A4, and A6. And a non-zero discriminant. So that's exactly what we have. This is already in MathLib. This is already a defined thing in MathLib. It's in one of the files in the algebraic geometry folder. So this is saying you have a discriminant, and an elliptic curve is just 5 coefficients, a discriminant, and a proof that the discriminant is really this value. Does that make any sense? Right, so but this is a curve. I just gave you the equation of the curve. What about the group? How's the group law obtained? I have not even stated what the elliptic curve is. I just stated the 5 parameters, the 5 variables. So that's so this is what is in MathLib. Anything after this is not yet in MathLib. It's currently ongoing some heavy scrutiny. But yeah, this is I want to now define the group, right? The group is basically a group of points. So a group of points, recall, is either 0 or an affine point. So if it's 0, basically I can do it in the inductive. Right? So inductive is either 0 or it's some point x and y with a proof that the point x and y lies on the curve. Okay, so maybe that is okay. Then now this inductive, I need to keep writing point ek. That's not so nice. So I use a notation ek. Yeah, so then I want to show that this using this definition, I can write down the group law, the identity, the fact that a group has negation, a group has addition, is commutative, and is associative, right? Stuff like that. So identity itself is very obvious, right? So 0 is the identity. Negation is also kind of easy. So negation of 0 is 0 by definition. Negation of this point, recall that negation just takes a point and then you reflect it about the x-axis. So what you do is you take xy and you send it to x minus y. Okay, but then now there's an extra term here because of technical reasons, but let's ignore that. Imagine it as flipping it over the x-axis. So what's this w thing? So w is a proof that x and y lies on the curve. So I need to supply a proof that x and this minus y thing lies on the curve. How do I do that? Well, I can take w, this w, which is this thing. I've replaced the x, right? I've replaced the x with x, so the x doesn't change. But I've replaced the y with minus y. So the minus y changes. This minus y, this minus y, this minus y changes. Oh, so note that only the left-hand side has y. The right-hand side doesn't have y. So I can just do a rewrite. So the x remains the same. The y changes. So after I do this rewrite, this expression here will be like y squared plus a bunch of stuff. And this thing will just be the same thing, but with y replaced with this thing. And then they happen to be equal by ring. Okay, so I tried to explain what a proof is in Lean by words. Maybe that's not very nice, but this is just the idea. The idea is that the majority of the work done in defining the operations are trying to prove that whenever you do something to a point, the point still lies on the curve. Yeah, so that's negation. But addition is very complicated. So addition is, let's see. You add 0 with p, you get p. You add p with 0, you add p. You take 2 points, which are affine points, non-zero points. What happens? So it's either 2 distinct points or 2 points that are the same, so you double a point, or the 2 points are the same, but they lie on a vertical line. So you get 0. Right, so I wrote some stuff here. So this is basically, L is the gradient of the line. Try to take the line and intersect the curve some point, and I get x3 and y3. Okay, the exact things here is not so important, but the point here is I can do it by equations. So I take x1 and x2, y1 and y2. The thing I get will be x3 and y3. What's the proof that x3 and y3 lies on the curve? Oh, that's complicated. So I put dot, 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 but this dot, dot, dot is like 100 lines or something. It's terrible. This is completely terrible. And now I have doubling a point, which is another 100 lines. Right, so the defining addition itself is already very annoying. So like I gave you a horrible definition of addition. Now, how do you check commutativity? Well, you have to first look at the cases where P and Q are either 0 or non-zero. And then if P and Q, they are the same point, then you do something. And if P and Q are not the same point, they're distinct, you have to do something else. And if P and Q are lie in a straight vertical line, you have to do something. So there are actually 6 cases. It's kind of doable, but each of the cases is like, I don't know, like 50 lines long. But I mean, this thing is kind of doable. It's not too bad. In fact, I have not actually done this because I know this is like doable, but it's not too bad. The problem here is associativity seems impossible. When you first try to do it, this has 6 cases. This has, I don't know, 30 cases or something. Because you have P, Q, and R, you have to look at all the possible ways you can add P, Q, and Q, R, and R, and P, and Q, and R, and P, Q, and R. All these possible scenarios. And that's very difficult, right? So, like this is currently it's not really doable. So the reason is, this is like a known difficult problem. It is a solved problem. People have done it, and people have given several proofs to do this because this is is known to be a difficult thing, right? So how many ways can you do it? So one way is to do it as what I said. I have like 20, 30 different cases and check all the cases one by one by solving equations. But apparently someone claimed that doing this step will require you to expand a polynomial with like 130,000 coefficients. So even with like just a bunch of coefficients, when you try to do like field sim or something, it times out. Like Lean, the tactic is not strong enough to do all these polynomial operations, let alone like 130,000 coefficients. There's a way to prove it using the theory of like elliptic curves over complex numbers. You have elliptic curves over a field, you try to embed that field in the complex numbers. Sometimes you can, sometimes you can't. When you can use this theory called uniformization. You can identify the elliptic curve group with some other thing which is clearly a group, and then you just do it. But the problem is we need a theory of elliptic functions which we don't have. There's a theorem. It's a theorem in classical geometry called Bezout's theorem and Cayley-Bacharach theorem. You can also kind of do this. Like you draw a bunch of curves, and then you say that, oh, if you have two cubic curves, they must intersect at exactly 9 points, and do something, some argument like that. This thing is maybe possible, but you need to define what it means to be to have higher multiplicity intersections. I don't think that's a thing yet in Lean, in MathLib at least. Then the most natural way to do it is not to do all these, but to identify EK with peak EK. So we have to define what peak 0 is. So the Picard group, recall, is like a bunch of divisor stuff. And you know that is a group. If you can identify the operations in the group law with that, then we can prove it automatically. We can prove that EK is automatically a group. Yeah, but again, the problem here is we don't have the Riemann Rock theorem. We don't have all these extra algebraic geometry notions. Right, so what's the current status? It's left as a sorry. I mean, I kind of given up. So I try to explain the problem, and I'm going to ignore the problem next. Right, so currently it's left as sorry, but I need to acknowledge that someone currently is working this out. They're using the first method, and it has been done. The last method here has been done in a different language, but only for characteristic f not equals to 2 or 3. So you're looking at the short form of the elliptic curve. Okay.
Then done by brute force because it's just smaller polynomials. Or
no, they actually define divisors, differentials. I think they did Riemann Rock, which I thought is quite amazing. Yeah. Okay.
For elliptic curves.
Sorry.
Only for elliptic curves.
Yeah. Yes. Yeah. Yes. Yeah.
I don't think they define the genus.
Yeah.
This is the proof I want to.
Yeah.
This is the proof I want.
I think this is probably the natural way to go. Not in general, but just for elliptic curves, sure.
Proof E of K is isomorphic to the class group.
Yes. Yeah. So I'm trying to. I explain the problem. Now I'm ignoring the problem. So suppose that I have already done associativity. What else have been done? So I kind of just assume that associativity is already a thing. Then you can actually do a bunch of other things if you already assume that it's a group. I've already proven that this association from F algebras to abelian groups is functorial. Right, so I can define a homomorphism for each map of F algebras. I can get a map of abelian groups going that way, and it respects the identity and composition laws. Given an extension L over K, you can equip it with the Galois module structure. L over K acts on this thing, and it can compute the invariance of the action. Right, the invariance is exactly E of K. So the E of K is exactly the image of the homomorphism under this functorial definition. There's also a notion of isomorphism of elliptic curves. So maybe it's not so clear, but I believe those are all the possible isomorphisms when you have an elliptic curve given in the equation form that I gave earlier, the Weierstrass equation form. So that's explicitly given by if you send that to that, the coefficients will change this way, and you can show that this is an isomorphism of groups. Yeah, so all the ... are just like I'm trying to ignore the proofs. So I've also done this thing called the two-division polynomial, which is polynomial is a cubic polynomial that has discriminant exactly equal to the discriminant of the elliptic curve. So what is this? This is saying if you have a point which is in E2, which means it gets killed by 2, then it is the x coordinate is exactly the root of this polynomial, and that happens to have discriminant, well, a scalar multiple of the discriminant of the elliptic curve. And knowing this thing, I can compute the structure of this thing. So this thing either has 0 points, 1 point, or 4 points. No, sorry. Okay. Anyways, it has at most 4 points, or exactly equal to 4 points. If it contains the splitting field of this polynomial, then it's exactly 4 points. Otherwise, you can only say that it has at most 4 points. So in other words, there's a point at infinity, and there are two torsion points. Right. So why am I doing all this stuff? So the aim was originally to prove this thing called the Mordell-Weil theorem. Like all the stuff I did earlier about the structure of this thing, the two-division polynomial, the isomorphisms, were like prerequisites to even try to do anything remotely close to proving this theorem. Right. So the theorem says that if you have a number field, a finite extension of Q, then that thing is finitely generated. So last week there was a talk on the structure theorem, and if you know the structure theorem, you can, if this is finitely generated, you know this is isomorphic to something that's finite times something, a bunch of copies of Z. The thing finite is called a torsion subgroup, and the number of copies of Z is called algebraic rank. So this was the thing required to even state the Birch and Swinnerton-Dirac conjecture, the BSD conjecture. Right. So how do you prove this thing? So it's essentially 3 steps. First, you prove that EK mod 2EK is finite. Right. So okay, if you know this is true, this is obviously true, right? By this. But if you know this is true, it's not clear that this is true. So for instance, if you have a group like R mod 2R is finite because R mod 2R is nothing, right? But R is not finitely generated as a Z module. So this is like this does not imply that obviously, but this implies this. So how do you show that this implies that? You need extra hypothesis, and the hypothesis is given by this thing called heights. So EK can be endowed with something called a height function, and at any abelian group endowed with such a height function, such that this thing is finite, must be finitely generated. So those are the 3 steps. So I'm going to focus on the first step because most of my project was trying to do the first step. I guess it's probably the more interesting one. I don't know. The last step is already done actually. This was done like a few months ago, completely abstractly with just an arbitrary abelian group. Then I'm gonna briefly talk about the heights at the end. Yeah. So weak Mordell-Weil. So we need to prove that EK mod 2EK is finite. And the way to prove it, well, there are several ways to prove it, but I'm trying to go to the proof as quickly as possible. And the way I want to use is this thing called the complete 2 descent. Okay, so remember that our elliptic curve is either the point 0 or a bunch of affine points satisfying an equation. So the first step is I want to kill off the A1 and A3 terms. So remember how we do that is that if K is a number field, it has characteristic 0, so it doesn't have characteristic 2 or 3, which means I can complete the square. And that's exactly what we do. So completing a square is an isomorphism given by a change of variables I did earlier. That's exactly just this. And if this is an isomorphism where E prime is the elliptic curve, but with these 2 things being 0, then this is finite if and only if that is finite, which means I can just show that that is finite to show that this is finite. Yeah, so that's the first step, first reduction step. So now I can just replace the first equation, the equation with A1 and A3 0. Right, so now the next step is what? What's the next step here? I want to reduce to the case where E of K already contains all the 2 torsion points of E, right? Which means K contains a splitting field of the 2 torsion polynomial, right? So E of 2, recall that E of 2, a point is in E of 2, if and only if the Y coordinate is 0. So if the Y coordinate is 0, I'm just saying I'm solving this equation. I'm looking at the roots, the 3 roots of this equation. And the 3 roots of that equation is exactly the roots of the 2 torsion polynomial. Right, so yeah, so what am I doing here? So okay, I wrote something here. I said let L be K adjoint this thing. So this is saying that I take K and I adjoin all the X coordinates of this, the X coordinates of the torsion points in this thing. So I let L be the splitting field of the 2 torsion polynomial. That's what I'm saying here. So it suffices to show that this is finite, implies that it's finite. Right, so if, well, how do I say this? So I'm saying that if I know that this is finite, then I can assume that if I assume that K already contains this thing, this is finite, then that implies that that is finite. Right. In other words, I can consider kernel, and I can show that if I just need to show that this is finite, because if I know this is finite and the kernel is finite, I know this is finite. So I'm just doing a bunch of like steps in like reduction steps in group theory. It's a completely elementary thing. Now this is the part which has some content, right? So this phi, this kernel, in fact, has a map to the set of homomorphisms from the Galois group L over K to E of L of 2. Right. So L is a splitting field of this thing. So this is like a finite thing. We computed the structure of this thing. It has at most 4 elements. So this is finite. So the homomorphism from a finite thing to a finite thing is finite. And if I can show this is an injection, this is also finite. And we're done. So I mean, one comment is that that thing looks awfully like a cohomology group. And that is a cohomology group. But unfortunately, we don't have Galois cohomology. So like I have to do everything explicitly. Yeah, so like after we do all this, we can replace the equation on the right with the roots of that thing, and where all the roots E1, E2, and E3 they lie in K. Right, so this is the code. I mean, I don't really have much else to say. I mean, the code is essentially what I said earlier, but instead of working over L equals a splitting field, I can work with any finite Galois extension. And instead of 2, it works for all n, except at the very end. So all the stuff here I wrote is for general n, but the last step here is only for 2 because I've only computed the structure of the 2 torsion subgroup, not all of them. Yeah, so now comes the so given these 2 reduction steps, I can express my elliptic curve equation as that, and with that equation I can define a map, sometimes called the complete 2 descent map, and it's a homomorphism from EK to 2 copies of K cross mod K cross squared. So what does it do? So it's a homomorphism. It must send the identity to the identity. It sends the point at infinity to 1, 1, because that's the identity. So that I send any point that's not 0, so x, y. I erase the y basically, and then I send x to x minus E1 and x minus E2. Okay, so first of all, these are classes in here. So it's not just an element. It's not an element of K. It's a class of this thing, right? But if I let x be E1, I mean, x can certainly be E1, right? If x is E1, then y is 0. So it's actually a valid point. What if x is E1? If x is E1, this thing is 0. So it's not an element in here. It's not an element of K cross. The way I fix it is I just let it be some other thing, which I mean, I don't really want to explain, but if it's E1 and 0, I just send it to this thing. And the second thing is okay, so I can just leave it that way. And same for E2. Right, so this map is, well, I just, basically the code is exactly what I said. I look at the different cases and I define this map to send it to them. So that's exactly what it's saying.
Why did you divide?
I could, yeah, so the actual code is not like this. I'm trying to simplify things to make it clearer. Yeah. Okay. Anyways, so okay, why am I defining this thing? Right. So I originally I want to show that this thing is finite. So what I'm planning to do is once I've defined this map, I want to show that the kernel of this map is exactly that thing. So there's an injection from EK mod 2EK to that thing, and I want to show that image is finite, and that's enough to prove that is finite. So I prove that the kernel is 2EK. Okay, so I don't really want to go into this, but on one hand, this is one direction is obvious, right? If you start from an element that is 2 times something, when you send over there, it's already inside here and here. So it's 1, so it's in a kernel. So this is obvious, but that one is actually not too bad. It's quite long, but for each element in here, you can construct an explicit element in EK that kills it. So that is 2 times it. Yeah, but it's a completely constructive proof.
So the only summary we've had so far is associativity.
So far, yes, yeah. Well, there are a few like minor things, but the main thing is just associativity. Okay, so the other thing, this is the second story that I cannot really fix. So I said kernel of delta is this thing, right? So I can compute this thing. Now there's an injection between the quotient of this thing into something. If I can show the image is finite, then I'm done. but I can't show it's finite. So the image, in fact, lies in a subgroup, which I'm going to call KS2. The subgroup of that thing, and this I can show is finite, but I can't show that this lies in here. That was the problem. I mean, I know it's true mathematically, but I can't show it in Lean because this thing depends on a set S of ramified places, or like bad places of K, including like the Archimedean places and a bunch of other horrible things. Yeah, like I think we are currently lacking like some of the theory of local fields to be able to prove this thing. I mean, it's kind of because like you can't even define. I mean, I guess you can kind of define what it means to have bad reduction, but like other than that, like you can't really prove anything. But I mean, mathematically, well, I hope mathematically it's true, but hopefully once we have done local fields, like this is not too hard. Okay, so like for the next slide, I want to like talk about what this is, right? So I just said it's some group, right? But then I want to talk about this thing because I said the elliptic curve is a group, but we didn't prove associativity, so this is not PRable. Right? And then this stuff is also not PRable because there's a sorry. But the definition of this thing and the fact that this is finite is PRable because this has nothing to do with elliptic curves. It's a completely like just, it's a subgroup of some kind of number field thing. So this is completely separate from the theory of elliptic curves. So I want to call it an interlude. So I let S be a set of finite places, and I want to define KSN, the n-Selmer group of K, to be exactly that subgroup. So a subgroup is the set of elements of the K cross mod nth powers such that I have a bunch of local conditions. So for each prime that is not in S, so S is a finite set, I'm saying all but the primes in here, the valuation is 0 mod n. Okay, so that's why I define to be an n-Selmer group. And I want to claim that this thing is finite. So how do we do that? So the first step is note that K empty set n is a subset of this thing, right? Because K empty set n means I don't have I have more conditions. So this is saying all the P not in S, but if I let S be empty, means this thing holds for all P. Okay, so how do I do that? I first write down a homomorphism. So what do? I take a class K, class X, and I send it to all the valuations at X for each P. Right? How many copies are there? Right. So for each P in not in S, it's 0. But for each P in S, it could be 0 or non-zero. So I just send it to something like this. Okay. So what's the kernel of this map? Well, the kernel of this map says, well, everything in P is already, everything in S is already 0. Everything not in S is already 0. And now I'm setting everything in S to be 0. So that's exactly the K empty set. Right. So again, if I know that this thing is finite, this thing is clearly finite, then I know this thing is finite. So I have this equivalence. Yeah, so and then this is basically, I mean, there's not much to say other than me like this literally writing down what I said earlier in Lean. So I guess there's this function here, val of ne 0 mod, which is a bit complicated to define. So I kind of just like ignored it. But this is exactly saying this thing.
How is define your finite set of places? How did you define that?
So these primes, not places. So I said places, but I guess I'm just looking at primes. So it's like height 1 spectrum. Yeah. Thin set height 1 spectrum or something. Right. So yeah. So this is exactly what I said earlier. Okay. So now this is the juicy bit, which I think is probably the most interesting part. So I want to show that. Now to show this thing is finite, right? How do I show this thing is finite? I can nest it in an exact sequence. So there's a thing here, which is the unit groups, the unit group modulo nth powers, and the class group. So these are like very fundamental objects in algebraic number theory. This thing somehow lies naturally in between these groups. Right? Again, there's a bunch of maps. So I can describe what F is, right? So K empty set N is a subgroup of this thing, right? So if you look at this thing and this thing, so how do you send an element from here to here? Well, first you take an element of this thing, or OK cross, you send it to K cross by just including it, take the quotient, that's okay, and then compute the kernel. The kernel is exactly that. So that's what F is. What is G? Well, G is complicated. I don't want to talk about it, but there is a map that is like well-defined. Right, so this is exactly what I did. I first define a map from OK to this thing, right? And then I show that the kernel of this is exactly the nth powers. So exactness, well, exactness just means this injects into that and the kernel of this is equal to the image of that, right? So I've shown that this injects into that by this, and I've showed that it's exact in here if the kernel of G is equal to the image of F. This thing is, I don't know, this is quite hard to prove, but apparently, yeah, I guess this is already done. Like, so yeah, so knowing that this lies in an exact sequence, I just need to, it remains to show that this is finite and this is finite. Yeah, so we prove that that is finite. Oh, but that's already done. This was done like 2 years ago. It's already in Mathlib, so I'm grateful to the authors. And the other thing is to show that this is finite. Oh, but how do you show this is finite? By the structure theorem, if you know this is finitely generated, this is finite. This reduces by the structure theorem to show that that thing is finitely generated. And this is the statement, well, it's part of the statement of Dirichlet's unit theorem, which is not done yet, and I need help. So I guess this is like the second story. But once this is done, everything is okay. Yeah, so I guess that's mostly it for weak Mordell-Weil, but I guess since I put the word Selmer groups, I want to like add a very small remark that there is a thing called the usual Selmer group that you might have heard of. It looks something like that. So I call this a Selmer group because this is in some sense like a two-dimensional version of the other Selmer group. This Selmer group is like a subgroup kind of that thing. But anyways, it's a remark that's like irrelevant. Yeah, so the other part was, I said there were 3 parts: the weak Mordell-Weil, heights, and using these two, I can use the descent theorem. We've talked about descent theorem, we've talked about weak Mordell-Weil. What about heights? So now I'm just going to give 1 page of like what is the current status. So what is a height function? A height function is a function from ek to the real numbers, satisfying 3 properties. First property being that if I fix a point q, then there is a constant such that for any p, the height of p plus q is basically the 2 times height of p up to this constant. With that inequality, right? And then the second property is that there is a constant such that for any p, if I double the p and I look at the height, it's close to like 4 times the height of p up to that constant. And the third property is that for any constant, the set of points with height at most that constant is finite. Okay, so a height function is just a thing satisfying these 3 properties. So this doesn't have to be E of k. This can be any abelian group. So just for any element in that abelian group, you have all these things. And that's how you prove like the general descent theorem for any abelian group. So what's the current status? The status is that I'm currently working on this right now for k equals to q, because for k equals to q, proving these 3 things is just a bunch of equations. You look at a bunch of equations, you plug them in, you solve for the inequalities. You write down the constants explicitly, in fact. This one is already done actually. For general k, personally, I mean, I've done like courses in elliptic curves, but nobody has ever done like at least in an undergraduate course, height functions over general number fields. I don't really know why that's the case, but I guess it's just more complicated. And I think there are some notions that we don't have, like we might require things like the product formula, which is like kind of missing. Product formula for like general k, as well as like some ramification formula. So yeah, but that's it. So the last slide here, I've just stated a bunch of potential future projects. So I defined 2 division polynomials, but by induction, you can kind of just do n division polynomials. And if you can define these things, you can do the structure of the n torsion subgroup. The weak Mordell-Weil theorem doesn't require n division polynomials. You only require 2. You just need to pick any number that's greater than 1. But I guess you can kind of define this in general, and this will be useful if you want to look at the structure of that thing. You can do like formal groups. There are these things called formal groups that feel like Lie groups, but not really. And if you have all these things, you can it's kind of useful by itself. It also helps when you try to do ellipticals over local fields. And now I stated like 4 things here, which we don't really have like a full theory of yet. And if we have all these things, then we can kind of define the things on the right here. Yeah, and then I guess I kind of ranked this in order of difficulty or timeline or something. Yeah, so I mean the last thing is to prove associativity. So we assume we do all these things, but we don't know that it is a group. Yeah, so I guess that's it. Thank you.
Thank you very much.